By choice or necessity, most people now live in cities where population growth, inward migration, and policies to limit urban sprawl are creating a more densely built urban environment. The quality of life in urban areas is determined to a large extent by continuing access to green spaces. Possibilities now exist for establishing greenery on a vast new area provided by the vertical surfaces of buildings. Green wall installations have become more noticeable over the last decade, but these installations remain confined to mostly prestigious locations, where their purpose is to support a corporate image or serve as a visitor attraction. Clearly, green walls are required to provide a spectacular visual impact or wow factor. The question is, can green walls be used to mitigate the lack of urban green space in the densely built urban environment? In my second presentation, I will examine the technology limitations, my attempts to develop systems that meet the requirement, and the new possibilities that may derive from such work. Scientific evidence supports the principle of using green walls on a large scale to adapt cities for climate change, provide a rich urban ecology, and enhance public health and well-being. The benefits of green infrastructure with such socio-environmental ambition are potentially immense, but as yet to be fulfilled. In my first presentation, I noted that substitute technologies existed for each green wall benefit, indicating competitive pressure. Market analysts have further suggested that the major constraint to future expansion of the green wall area is a perceived unreliability of the current planting systems. The requirement is for green wall processes that are technologically effective and economically efficient. Green walls consist of modular units containing organic or mineral root substrate and an irrigation system supplying a balanced mixture of plant nutrients. The designed serviceable life of modular green walls is ideally required to match that of the building they cover, with plants replaced at intervals as they die or become overgrown and difficult to maintain. Designs for green wall assemblies have proliferated, but few, if any, feature inventive steps for maintaining optimized root conditions essential for healthy plant growth. A green wall may fail due to the irrigation system, causing complete loss of the plants. There is very little margin for error due to the restricted root volume. For this reason, green walls are often over-irrigated and may become water-saturated, which restricts the range of suitable plant species. The substrates in which the roots grow may consist of organic composts, which gradually decompose, lose favourable hydraulic and nutrient properties, and eventually erode. Sometimes inadequate management of the irrigation or plant nutrition produces a green wall that doesn't bear close inspection. Ideally, a living wall planting system should ensure optimum root moisture conditions are maintained automatically and should be adaptable for different plant species, artistic arrangements, and biodiversity. Pollution from discharge to drainage should be eliminated, and methods of production and operation should minimize the cost of ownership and enable simple and timely maintenance. These requirements provided the goals for further development. Irrigation should match the rate that water is lost from the plant leaves by the process of transpiration. Transpiration varies dynamically with factors in the soil, the plant, and the state of the weather. Ways of calculating the correct timing and amount of irrigation, known as irrigation scheduling, has been researched over many decades for farm crops, including in my own doctorate studies and subsequent collaborative research on farms in the UK and on the European continent. The solutions I helped develop are based on continuously monitoring the soil and aerial environment and using these measurements to calibrate computer models that simulate the flow in the soil, plant and atmosphere system. By adding weather forecasts, they can predict irrigation requirement for days in advance. Part of my contribution has been in the development, manufacture and use of electronic sensors for monitoring the water status of soils and plants. A soil moisture sensor that I developed in partnership with specialist contractors is readily calibrated for solid mineral fibre substrates that are widely used for long-lasting green wall systems, where it shows a full range sensitivity and an excellent dynamic response. The sensor I developed works on a thermal principle in which moisture is inferred from tracing the passage of a heat pulse. It's the same principle that applies when wet soil feels cooler to the touch than a dry one. Other types of sensor infer moisture from soil electrical properties and may be affected by fluctuations in background temperature or by the dissolved salts present in hydroponic substrate systems. These factors don't affect the thermal properties measured by my sensor. The associated electronics provide sensor excitation, signal capture, data processing and built-in serial data communications, enabling sensor networks. The measurement and modelling approach could be adapted for precision irrigation of green walls, as I described in an article I wrote for a trade journal in 2011. But further work led me to pursue a different approach, which is outlined in the next few slides. The irrigation requirement for green walls is highly variable. Exposure to air movement at higher elevations can be extreme. This affects the potential evaporative demand, as demonstrated by my calculations for a tall building in Japan, based on a published dataset of environmental measurements. The variability at pavement level will be chaotic due to partial solar shading, heat radiation from pavements, and turbulent air flows. The water supply to the plant roots may also be subject to rapid decreases due to the highly porous nature of the substrates in which the plant roots grow. While none of these problems is insurmountable, they could invalidate many of the assumptions that are generally applied in simulation models developed for use in field crops. The key finding was that large gradients in moisture developed between the upper and lower tiers of substrate blocks within the module. This was discovered by continuously monitoring the substrate moisture with a vertical array of sensors during cycles of irrigation. While the upper tiers drained quickly, indicating a requirement for irrigation, the base tiers remained close to saturation. Soil moisture sensors have been proposed for direct monitoring of irrigation requirement, but this is complicated by the moisture gradients within modules and the potential for chaotic variability between them. It will never be practical to monitor more than a few modules or locations within modules for more than short periods. It may be possible to determine a minimum number and placement of sensors using just a few measurements to calibrate a computer model, which is then used predictively for irrigation scheduling. However, the tasks are time-consuming and require specialist inputs. The solution that was eventually devised uses the specific moisture characteristics of the substrate and the design of the module to provide self-adjusting substrate moisture. Water is loosely held in the wet substrate by capillary forces. This force depends on the pore space between and within the substrate particles. It exerts a negative suction pressure or tension measured in kilopascals or kPa, which relates to the volumetric moisture content by the moisture release curve and is shown for different types of substrate. Another way of expressing moisture tension is with head of water measured in units of length, which indicates that it can be manipulated by geometry. The self-adjusting principle for substrate moisture is realized with a block of dense mineral fiber substrate and an arrangement of moisture wicks, connecting it to two water reservoirs, one above the block and one below it. The top reservoir drains rapidly into the block by a siphoning effect. The base reservoir provides a slower adjustment flow in either direction, up or down. The balance of these flows tends towards an equilibrium moisture within the substrate. When substrate moisture exceeds the limit defined by the distance between the block and the base reservoir, there is drainage into the base reservoir. When moisture is lost from the substrate by the process of plant transpiration, it is replaced by upward flow out of the base reservoir. In certain conditions of extreme evaporative demand, it's conceivable that transpiration might exceed the rate that water can flow to the roots through the substrate and the wick, potentially leading to plant water stress. However, such stress is prevented by the capability for rapid rehydration provided by the siphon pathway. This mechanism also enables periodic flushing of unabsorbed salts that could otherwise accumulate in the substrate to levels that might be harmful to the plant. A viable production prototype was constructed from mostly standard PVC profiles, which were machined by specialist engineers and assembled by solvent welding. The two water reservoirs, one located above the rectangular substrate block and one below it, were linked by two side channels. During an irrigation event, the top reservoir is filled and overflows down the side channels to the base reservoir, which in turn fills and overflows through an internal overflow channel, providing a cascading flow through the entire column of stacked modules. The design enables the equilibrium substrate moisture to be set for a plant species using module geometry. By this means, plants requiring different optimum moisture can be grown adjacent to each other within any planting arrangement. The work required development and testing of manufacturing procedures and all aspects of complete systems. A building was provided for this purpose with spaces for a workshop, material storage, office and a yard for plant raising and systems testing. The sponsor was the owner and property developer for the former Shrewsbury prison. The intention was to provide green walls for the main site, fulfilling a central horticultural theme planned for the redevelopment of the prison for residential and business uses. A simple, low-maintenance irrigation system with effectively zero emissions to drainage was achieved with a circulatory flow of fresh nutrient solution between the green wall and a mixer tank. The mixer tank was kept topped up with a balanced nutrient solution fed from a mechanical diluter, supplied in turn from a rain tank and a concentrated stock solution. The nutrient solution was pumped from the mixer tank under timer control to a header pipe at the top of the green wall, where it was distributed through emitters maintaining a constant flow at the top of each stacked column of modules. The return flow to the mixer tank consisted of excess fresh nutrient solution from the emitters and from the base of each column of stacked modules once all the module reservoirs had been replenished. The only further process required was periodic flushing of the modules with high-frequency irrigation and emptying of the mixer to a grassed area or flower bed. Irrigation events were triggered by activating the mixer pump under time switch control. The remaining electronic controls simply maintained fluid levels in the mixer tank and in the rainwater storage tank, and in this case they switched between irrigating living walls and the hydroponic nursery. The electronic components consisted of level sensors, smart relays and associated voltage regulators. A large installation requiring multiple irrigation zones would be operated by a programmable logic controller. Small green wall installations were operated successfully over several seasons with a narrow range of plants including heucheras, sedges, persicaria and a few other species. The system was intended to be scalable for larger installations. So the next stage of the plan was to develop and test the design and procedures in a multi-story demonstration. But before this could be achieved, the property owner decided to put the property up for sale, citing market reasons connected with Brexit uncertainty. Plans had been advanced for green walls covering the surface of the prison gymnasium. This anachronistic building, adjacent to listed prison structures from the Victorian era, required aesthetic restoration. Preparations included consulting a structural engineer on the framework design, establishing a module fixing method, and testing the brickwork for integrity. Abstract planting designs were prepared by me to illustrate the effect of softening the building's rectangular shape, echoing the roof angle of the adjacent Victorian buildings and the distant slopes of the Long Mynd Hills. I also included an architectural feature representing Charles Darwin's Tree of Life sketch, reflecting his local birthplace. Final designs would have been prepared in consultation with the client and professional landscape designers. The zero-waste irrigation system shown in the schematic was intended to supply all green areas on the site and to divert the waste from periodic flushing of the wall system for use on conventionally planted areas. Other potential sites for green wall demonstrations in Shrewsbury were also under serious consideration. Estimates of costs for the Dana project were prepared using supplier quotes for production materials, outsourced machining and labour for assembly and installation. Quotes were also obtained for a method of volume production by injection moulding, enabled by the small module dimensions. The volume production method achieves considerable savings over the machined version, even when accounting for replacement of tooling. Continuing development may enable further possibilities for engineering out costs. These figures exclude groundworks and capital installations, which are site-specific. They also exclude compliance with new buildings regulations that are likely to be introduced by the ongoing inquiry into the Grenfell Tower cladding fire tragedy. I envisage future embodiments of the novel green wall technology will comply with all regulatory standards. Operations for maintenance and management are essential to maintain the plant display quality, ensure continuing efficiency, and prevent failures of the irrigation system. The lightweight module is simply detached for inspection and replacement of capillary wicks, or rearrangement or regeneration of planting designs, and seasonal replanting if required. The balanced nutrient solution is a consumable item prepared as a formula concentrate and restocked as required. Nutrient diluters are mechanical components that require inspection and servicing according to manufacturer instructions. Inline filters need to be cleaned or replaced to maintain irrigation flow, and the electrical and electronic components require periodic servicing or replacement. Additional protection for large installations may be provided by electronic sensors and internet-linked warning systems. Pressure sensors can detect the operation of an irrigation valve and the efficiency of an inline water filter. Strategically placed moisture sensors may be used to check the substrate moisture levels, and areas of plant water stress can also be detected remotely by infrared thermometry of the plant canopy, which is another technique that I've helped develop for use in agricultural crops. Linking sensors to the internet is an existing technology. Management decisions could also be improved by including artificial intelligence. In future, maintenance operations at height, such as pruning or module replacement, could be automatically carried out by climbing robots. Novel design concepts based on the planting module have been realized or envisaged. The next few slides illustrate some of the possibilities. An indoor green wall was produced with miniaturized irrigation system components and backing channels for protection of interior walls. A module enclosure was devised to enable modification of the plant aerial microenvironment, as well as providing an architectural element in its own right. It was inspired by limestone rock formations of the Burren National Park in Ireland, which create a unique thermally protected environment, supporting a broad and unusual mixture of both Arctic alpine and Mediterranean plants growing side by side. The reconfigurable modular concept permits inclusion of architectural features, plain facade elements, and habitat units for wildlife. It increases the scope for artistic expression by enabling planted modules and architectural elements to be exchanged, repositioned, or replaced without reconfiguring the irrigation system. The concept extends to three-dimensional designs, aquatic habitats, and units for a wide range of plant species as well as animals such as insects, birds, mammals, reptiles, amphibians, and even fish. Another concept is to adapt planting modules for removing air pollutants using deposition to both the plant canopy and the plant roots. I outlined this concept in Talk 1, including my development of the deposition theory, which could be used to aid optimization and evaluation of module designs. Yet another concept is to divide the plant roots between two module compartments, which are alternately irrigated and allowed to dry out to impose partial root dehydration, which has been shown to induce a dwarfing habit in some vigorous species, reducing the pruning requirement and increasing irrigation use efficiency. Finally, the module design could also be adapted for sloping roofs, with one conceivable application being an ammonia scrubber for use in intensive animal production units. So the work I've done to date has identified the modular green wall irrigation problem and provided a design solution that optimizes substrate moisture intrinsically and passively and avoids irrigation runoff into the drainage system. The modular design also provides versatility for planting arrangements and a range of environmental services. The requirement remains to build a scaled-up demonstrator which will perfect and verify all the component systems and procedures in a large installation, and to exploit the considerable scope for development and evaluation of the many novel configurations that have been indicated. Also, there are opportunities to address questions of fundamental interest to the public with research on public health and environmental value, economic efficiency, and potential use of government instruments for market intervention. I believe that implementing these developments would create a better quality of life within our densely built urban environments. To make further progress, I am seeking collaborations to fulfill 3 requirements: an institutional base for the development work, sponsorship and site for a full-scale demonstrator, and commercial partnerships providing a route to market. So to finish, I would welcome inquiries in any of these areas, or any queries or suggestions anyone cares to make arising from my presentations.